The title of my talk is Scanning Nonlinear Direct Microscopy Nanoscience Technology for Next Generation Ultra-High Density Ferroelectric Data Storage Beyond Hard Disk Drive and Flash Memory. My name is Yasuo Cho from Research Institute of Electrical Communication at Tohoku University, Japan. And this view shows the research motivation of this study. As you know, total global amount of digital data was 6.1 zettabyte in 2016, but it is expected that it will reach 163 zettabyte in 2025, and such huge total global amount of digital data cannot be stored only by using the conventional magnetic hard disk drive. For example, this graph shows the ARL decode density of the magnetic hard disk drive, and it saturates at 1 terabit per square inch. So, as an alternative technology, novel data storage devices are required to withstand with the massive increase of digital information. And this figure shows a comparison between the ferromagnetic domain wall and the ferroelectric domain wall. In the ferromagnetic crystal, due to the exchange interaction, the domain wall thickness is a little bit large. On the other hand, in the ferroelectric crystal, the domain wall thickness is very thin because there is no exchange interaction in ferroelectric material. And we actually measured the CC domain wall thickness of the PZT thin film by using our special scanning probe technique named Scanning Nonlinear Direct Microscopy SNDM and obtained this result. So actually measured CC domain wall thickness of PZT is 1.9 nanometer. It is 3 or 4 lattices. So the domain wall of the ferroelectric is a few lattices. And this is favorable for the data storage application. And on the other hand, we have developed Scanning Nonlinear Direct Microscopy SNDM. And originally, this microscopy technique was developed for the measurement of the ferroelectric domain through the measurement of the capacitance variation caused by the nonlinear direct response. And as this microscopy technique has a quite high sensitivity of the order of the minus 10 to the minus 20 seconds. So using this technique, we also have succeeded in visualizing stored charge in semiconductor device. Moreover, under the ultra-high vacuum circumstance, we can measure the dipole moment with atomic resolution by using the SNDM. And this figure shows the principle of the SNDM when we measure the ferroelectric polarization. This equation shows the polynomial expansion form of electric displacement as a function of electric field E3. The PS means the spontaneous polarization, and the expansion coefficient epsilon2 is a linear dielectric constant, and epsilon3 is a nonlinear dielectric constant at its third rank tensor, and epsilon4 is a higher order nonlinear dielectric constant, and this is a fourth rank tensor. And even rank tensor, including a linear dielectric constant, it's a second rank tensor, is insensitive to the state of the spontaneous polarization. On the other hand, this epsilon3 is very sensitive to the state of the spontaneous polarization and crystal anisotropy because it's a third rank tensor, odd rank tensor. As you know, there is no odd rank tensor in the isotropic material with center of symmetry, and its sign changes in accordance with the inversion of the spontaneous polarization. So, if we can detect epsilon3 only separating from the response of other order nonlinear dielectric constant, we can obtain the information of the spontaneous polarization. To detect the epsilon3 only, actually speaking, we apply the sinusoidal electric field with amplitude EP and the angular frequency omega p to the material to be measured. And if we apply this electric field to the capacitor made of the material to be measured, alternate capacitance variation occurs. And alternate capacitance variation related to epsilon 3, which contains the information of the spontaneous polarization, is directly proportional to the applied field bearing with the same angular frequency omega p. And higher order response is proportional to the square of the applied field bearing with doubled frequency to omega p. So by using this frequency difference and using a lock-in technique, we can simultaneously and individually detect the epsilon 3 and epsilon 4. And this view shows a schematic diagram of SNDM. Here is the SNDM probe, which consists of the so-called free-running active LC oscillator whose oscillating frequency is tuned to this LC resonant frequency. The typical oscillating frequency of this SNDM probe is a gigahertz order. And the metal tip is connected to this LC resonant circuit. And then from the outside, we apply the sinusoidal voltage between tip and sample. The typical frequency of this sinusoidal voltage is from the 10 kHz to 100 kHz. Anyway, by applying this sinusoidal voltage, tip sample capacitance is modulated. Then frequency modulation signal comes from this SNDM probe, whose frequency deviation is proportional to the capacitance variation occurring under the tip. And using FMD modulator lock-in amplifier, we can detect this frequency deviation. By setting the reference signal of the lock-in amplifier at the fundamental frequency of omega p, we can detect the epsilon 3 only. And then we conducted the study on ultra-high density ferroelectric data storage. Of course, in this study, we use scanning nonlinear direct microscope as a read-write device, and also we use a lithium tantalate single crystal PZT thin film and so on as a ferroelectric data storage medium. And this is a ferroelectric data storage based on SNDM microscope. And the ferroelectric medium is on the linear piezo scanner. Anyway, when we write the domain dot or domain information, we apply the relatively large voltage pulse to the ferroelectric recording medium to inverse the domain dot locally. And when we read the formed domain dot, we simply use SNDM technique. And at first, using this system, we investigate how fast domain can be switched. In this case, we used the very thin lithium tantalate single crystal with a thickness of 18 nanometer, and we applied the very short pulse with a duration of the 500 picosecond, and we can succeed to reverse the domain dot. This means short domain switching time is suitable for the development of high-speed gigabit per second order storage system. And next, we investigated how small nanodomain dot can be formed. And then we obtained this small nanodomain dot. In this case, we apply the pulse voltage with a amplitude of 8 volt and duration of 10 nanosecond to the sample with a thickness of 30 nanometer, and obtained nanodomain dot size is 3.8 nanometer. If we can form another dot in the vicinity of this dot, the corresponding memory density will reach 80 terabit per square inch. But actually speaking, it is somewhat difficult. Next, to demonstrate the ferroelectric data storage is surely rewritable. At first, we formed 6x6 nanodomain dot with the size of the 15 nanometer. And then we selected 6 dots along the diagonal line and apply the voltage pulse with opposite sign to erase the 6 dot and obtain this result. From this result, you can understand the ferroelectric data storage with a memory density of terabit per inch plus is surely reliable, and we can freely control the nanodomain dot with the size of the 15 nanometer in diameter. Then we form the nanodomain dot array by varying the pitch of the between the two dots. From the 6 nanometer to 14 nanometer. And then we obtained this result. In this case, the dot size is 7 nanometer. The corresponding memory density of this dot array is 13.2 terabit per inch. And, above mentioned fundamental study predict the ferroelectric data storage is surely high density recording, but this does not necessarily mean actual information storage requiring the abundance of bits to be packed together is easy to achieve. So to demonstrate the actual information recording, we stored this information to the ferroelectric lithium tantalate single crystal like this, and this is a result. And from this result, you can understand we succeed to store the information with a bit space of the 12.8 nanometer. The corresponding memory density is 4 terabit per inch. So you can understand we have succeeded in actual information recording at the 4 terabit per inch. And next, instead of the ferroelectric data storage system using the linear piezo scanner to improve the read-write speed, we newly developed the hard disk drive type ferroelectric probe data storage test system like this. And reading and writing mechanism is the same as the SNDM ferroelectric probe data storage test system using the piezo scanner. And anyway, using this HDD-Type SNDM data storage system, we investigated how fast the domain dot can be written. And we write the domain dot at the speed of the 20 megabps, 50 megabps, and 100 megabps. And anyway, above 50 megabps, we failed to form the nanodomain dot in some area, but at the 20 megabps, we succeeded in forming the nanodomain dot without any deficiency. So from this result, you can understand we have succeeded in 20 megabps data writing. And also we conducted two forms high density data recording using the hard disk drive type test system and obtained this result. In this case, dot size is 13.7 nanometer in diameter, which means we have succeeded to store the domain dot with the error decode density of 3.4 terabit per inch using the hard disk drive type test system. And moreover, using the HDD ferroelectric data storage system, we stored actual real information SNDM using the ASCII2 code and obtained this result. This is a SNDM image of the actually stored SNDM, and this is a reproduced signal. So we have succeeded in reproduce the actual information SNDM by using the hard disk drive type SNDM probe memory. And finally, we investigate how fast to read the ferroelectric domain by using the HDD ferroelectric data storage system. And in this case, rotating speed was 600 RPM. And we read such a domain pattern with the size of with the pitch of the 2 micrometer and obtained this result. So corresponding positive and negative signal was clearly reproduced. And corresponding bit rate of this reading is 3.72 megabps. And even though this bit rate is too low than commercial values, but this value is quite high speed in comparison with other ferroelectric probe data storage, for example, using the piezo response force microscopy. But anyway, we have to improve the readout speed. To do so, we need the large epsilon 33 nonlinear dielectric constant medium. And lithium tantalate has a lithium tantalate single crystal has a epsilon 33 of 0.73 at farad per volt. On the other hand, PZT have a large epsilon 33 value of the order of the 50 at farad per volt. So the epsilon 333 value of the PZT thin film is 70 times larger than that of lithium tantalate. So by replacing the lithium tantalate with PZT, we can prospect the high speed readout at the gigabps order in the near future. In conclusions, several experiments for developing ferroelectric probe data storage were conducted using the SNDM scanning nonlinear direct microscopy and obtained the following result. At first, domain dot with a diameter of 3 nanometer was written on lithium tantalate single crystal. The corresponding memory density of the 3 nanometer diameter is 80 terabit per square inch. And actual data bit array with a LL decode density of 4 terabit per square inch was written on the recording medium. Also, domain switching time can be decreased down to 0.5 nanosecond using an ultra-high thin 80 nanometer thick recording medium, and the corresponding writing speed is 2 gigabit per second. And also read-write demonstration using hard disk drive type test system were conducted and obtained result of writing speed of the 20 megabps and reading speed of 3.72 megabps and recording density of 3.4 terabit per square inch. Finally, by replacing the medium with PZT, improvement in readout speed gigabps order will be achieved in the near future. Thank you for your kind attention.